So at the conclusion of the hypothesis test about the pineapples from the 9.3 video, I talked about I wanted to make a third video for how confidence intervals relate to these hypothesis tests. So let's just think about what we calculated in the pineapple problem really quick. So that was a two-tailed test. It's a t-distribution, but it looks normal, right? Same thing. And we got some really small p-value. I think it was 0.008 or something like that. Something very small. And we rejected the null. So we said that the mean weight of the pineapples was different. That's all we conclude. We could say it wasn't 31 ounces. It's different from 31 ounces. Well, that doesn't really tell the manager if this irrigation system is doing better or worse. Like if the mean increased, if the mean was over 31 ounces, it obviously is doing better, right? The pineapples are growing bigger. If it's less than 31 ounces, that means the irrigation system isn't doing as good. So maybe he decided to change it. So what we can do to kind of get a better idea of whether it is better or worse is we create a confidence interval around that sample mean. And here, one is done for us. So here's another mini tab that's a computer output for a significance test and a confidence interval based on this problem up here. So let's look. So here's my test. Here's the p-value. We didn't spend a lot of time on printouts. I'll include some in the notes folders, but the p-value's right there. Here's my 95% confidence interval. And think about why 95. Well, in my two little tails here, we were basing this on alpha equal to 0.05, meaning we wanted to know if that area was less than 5%. That means this middle area was 95%. So they're kind of go hand in hand, the 95% with the rejection of alpha equal to 0.05. And here's my confidence interval. So how we'd conclude, in the last chapter, we would make a conclusion here that the true mean weight of pineapples, or we're 95% confident that the true mean weight of these pineapples in this large field is between 31.255 ounces and 32.616 ounces. So, I mean, based on this confidence interval, it's showing that the irrigation system has increased the weight. Because remember, the null hypothesis was 31 ounces. 31, somewhere over here, was less. So these pineapples are bigger. Proportions works the same as it does for means. So you could do the same thing with a confidence interval and a stat test. I could have done it in the calculator. Let me rewind real quick. I could have went to the calculator to do this and did a menu, statistics, confidence intervals, and we could have did a t-interval. We had stats. I have to go back and look at all the information. The X bar here, I think, was 31 point. I gotta go back. 31.935. Standard deviation was 2.394 or 934. Let me double check. 394. The N was 50, and we're going to do a 90%. I could have got that same confidence interval this way. Where'd it go? Stats. Sorry. 31 point. Forget again. I'll have it memorized by the end of this. 935. 2.934. Make sure again. 394. N was 50. Press enter this time. And there's that same confidence interval. So you could have calculated that yourself, even if you didn't have a computer output. And let's scroll on a little bit. So one last thing to mention here. Confidence intervals and two-sided tests go hand in hand. What they do is the confidence interval just gets a little bit more specific than it does with just the stat test. And typically we're going to do it with means here. With proportions, it ends up being a little bit different with the alpha levels. But sometimes they're asking you to calculate both the stat test and the confidence interval. That way you can relate or get a little bit more specific with your result. One more thing I noticed I missed from 9.3 is inference for means with paired data. No real difference in the procedure, but paired data, if you remember back to when we did a matched pairs design, for instance, in an experiment, a lot of times before and after, you pair similar individuals. So here, with paired data, you would take those paired results and you would subtract them and you get a new list. So let's look at how this looks real quick in an example. And before I move on, actually, we're going to be interested in, it's going to still be a T procedure, but now it's going to be mean difference, and they're going to call it mu D. That little d just means difference. So here's an example of paired t-test. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent. Each subject was barred from coffee, colas, other substances with caffeine. During a 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took a placebo. The order in which the subjects took caffeine and the placebo was randomized. So we don't have a random sample here, but this randomized treatments here is going to make sure it's okay in this experiment. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. So here are my results. So here are my 11 subjects. This was their level of depression with caffeine, and this was their level of depression on the placebo. And then notice, they found a difference. They want to know a mu D. And here, if they do caffeine minus placebo, let's think about that. No caffeine, that means this number would have to be bigger. We're going to be looking for negative numbers. So our alternative is going to be, well, is it less than 0? No difference, my null hypothesis would have been, I'm just going to assume there is no difference. I'm going to assume the difference is 0, right? If caffeine doesn't affect depression, I would assume when I subtract these numbers, I get 0. If I think that caffeine, or being deprived, so no caffeine increases, I'm going to expect each of these to be a negative when I subtract. And let me correct myself really quick, because I noticed they didn't subtract from left to right. They're subtracting placebo minus caffeine. So let me cross those out. So here my null is still no difference. But my alternative, I assumed they were going to go from left to right, but they didn't. Placebo minus caffeine, if that's greater than 0, meaning if I subtract, I get a positive number, that's going to mean there was more depression on the placebo, right? Placebo is higher. I would get a positive number when I subtract, going right to left. And then from there, the test works exactly the same. The conditions are the same. It's just on the differences. So let me scroll back here. I would check the conditions based on these differences. And here they're met. Random's met because they randomly assigned treatments. The only problem here is I can't make inferences to the population. I can just infer to these volunteers. The normal condition, they made a histogram, they made a box plot and a normal probability plot, and they said it was normal. And then independent was met. And then even my t-test is the same. I mean, here I would have entered that column in a list and spreadsheet. I would have entered the differences, whatever I got for placebo minus caffeine in one column, and I would have done everything else the same. I get this p-value of 0.002, 0.003 if I round. That is less than the alpha of 0.05, so we would reject the null, and we would say that depriving caffeine or these volunteers of caffeine caused an average increase in depression.